Respected presenters, dear participants, ladies and gentlemen, the subject of my presentation is economic development a cause of astronomy investments. Global context. The rise of the space economy. Over the last 20 years, there has been an unprecedented research in global space and astronomy activities. This period is characterized by both an increase in ambitious public projects and private sector participation. OSD 2022 data, the estimated budget allocated by member country governments to space programs has reached 75 billion USD. Strategic importance. Astronomy is no longer just scientific curiosity but has become a critical spending item in national science and technology portfolios. Research question and problem. Is a country's level of economic development a causal factor triggering public investment in astronomy research, or are these investments a precursor to economic development? This study aims to empirically resolve this classic causality dilemma in the literature using panel data, econometrics, and Granger causality tests. Core hypothesis: discretionary spending. The hypothesis at the center of the study is that astronomy and space research are of the nature of discretionary spending. Public good. Astronomy is non-excludable public good whose benefit emerge in the long term. Welfare threshold. Countries can only allocate resources to this area after meeting essential expenditures such as education, health, and infrastructure. Vulnerability, being one of the first budgets to be cut during economic crisis, indicates that these expenditures are dependent on economic welfare. Literature, R&D, and economic growth. Economic growth theories view technological progress as the key to prosperity. Endogenous growth theory. Roemer and Egan and Howitt argue that growth stems not from exogenous factors but from endogenous dynamics like innovation and knowledge accumulation. Empirical evidence. Countries like Israel, South Korea, and Germany allocation percent 2 and 4 of their GDP to R&D supports the positive correlation between R&D and growth. Development level effect. In developing economies, public R&D can trigger growth more strongly by playing a crowding in role for the private sector. Literature, science funding and spillovers. Determinants of science funding. Science budget differ from statutory entitlements as they are determined in individual budget processes. These expenditures are highly sensitive to macroeconomic conditions. They compete for resource with other strategic areas such as defense, health, and energy. Economic spillovers. The reverse causality arguments defends that astronomy creates economic value. Technology transfer. CCD sensors, Wi-Fi, medical imaging. Human capital. Development of the data analytics and engineering skills. Direct impact. Observatory construction and operational expenditure. Dataset and variables. The analysis use a balanced panel data set covering the period 2000 and 2025 and including 35 countries. This variable code and definition and source. This variable astrospend dependent variable natural logarithm of public budget allocation for space exploration and utilization. GDP K-dependent independent variable natural logarithm of GDP per capita economic development indicator. HDI Alternative Development Indicator Human Development Index Income, Education, and Health. In total RD, this control variable, share of total RD expenditure in GDP, control for country general science vision. This table 1, descriptive statistics. The high standard deviation and wide range in astronomy expenditure indicate significant gaps between countries in terms of resource allocated to this area. This diversity is the key factor making panel data analysis meaningful. Econometric model panel data analysis. Model step. The fixed effects model was chosen to control for unobservable country-specific effects. The model equation is ln astro equal to beta and ln GDP and controls and error variable. Analysis step 1. Cross-sectional depends. Testing interaction between countries. 2. Unit root test. Ensuring stationary. IPS test. 3. Model selection. Fixed and random effects. Hausman test. 4. Causality. Determining the direction of the relationship. Dumitrescu and Hurley. Table 2 and 3 Diagnostic test. Cross-sectional depends. Hypothesis 0 is rejected. There is depends between countries due to economic shocks or policy spillovers. Therefore, robust standard errors were used. Panel unit root test, IPS test. Variables are not stationary at level values, however, they become stationary when their first difference are taken, which is suitable for causality analysis. This table for panel regression results. The table provides that economic development has a strong and positive effect on astronomy investments. According to Model 1, a %1 increase in per capita income leads to approximately and percent 0.85 increase in the astronomy budget and our square root value of percent 71 indicates that the model has high explanatory power. Detailed analysis of regression findings. Income elasticity. The coefficient of 0.85 indicates that astronomy spending is sensitive to income but does not fully reach luxury good elasticity. Nevertheless, these expenditures tend to grow in parallel with income. Human development effect. It is interesting that the HDI coefficient is higher than GDP. This shows that not only money, but also on educated population and health standards form a critical infrastructure for scientific investments. General R&D relationship. The significant effect of total R&D expenditure confirms that astronomy is not an isolated effort, but developed as part of the country's general innovation ecosystem. Table 5. Dumitrescu-Harlin panel causality. The test results are extremely clear. There is strong causality from both GDP and HDI to astronomy expenditure. However, no statistically significant causality was found in the reverse direction from astronomy to development. The relationship is one way. Discussion of causality findings. Why? This finding does not mean that astronomy has no economic benefit. It simply shows that these benefits are too long-term and indirect to be seen instantaneously in macroeconomic data. Granger causality is about predictability. A country's wealth today predicts its space budget tomorrow very well. But today's space budget alone cannot explain tomorrow's wealth. Conclusion and policy recommendation. Developing countries. Strategy, economic foundation first. Science development is a prerequisite resource should first be allocated infrastructure and education. For astronomy, participating in international consortia is the most rational path rather than high-cost isolated projects. Developed countries, strategy, sustainability. Science investments are sensitive to economic fluctuation. Long-term autonomous funding mechanism should be established to project this project from political and economic conjunctures. General approach. Strategy integration. Astronomy should be seen not as an isolated prestige project but as part of the national innovation system. Spillover effects should be maximized through industry collaborations. Thanks for listening.